slides.
Okay, so cool. I'm sure a lot of people will be trickling in later on because our other workshop for React is still ongoing, I believe, but that should be ending soon. But so hi everyone, and welcome to Intro to Computer Vision. I hope you guys are enjoying yourselves so far. But yeah, so for the next half an hour, our speaker will be talking about computer vision. And I just want to go over some quick code of conduct issues. So if you guys have any questions, try to drop that in chat, and other Angela will be moderating that. So try not to unmute yourself and popcorn those. Please do not interrupt the speaker. We'll be sure to get to any of your questions. And also, if you guys are arriving late, and this applies to future events as well, please don't ask the speaker to repeat a whole section. We will have a recording put onto our YouTube. So if you guys are late, if you guys have missed something, you can always refer back to that. But yeah, so just try not to interrupt, and we'll make sure to get all your questions answered. So without further ado, I'll hand it over to our speaker today.
Hello, everyone. My name is Anshuman, and as you can see, I'm a senior machine learning engineer at Bensai. And computer vision is actually one of the more fun parts of my job. So I'm like very excited to talk about it and hopefully show you guys a different perspective on, other than the trends you see out there for computer vision. So let me share my slides. I think you need to allow me to share my slides. Yeah, there you go. Can everyone see it? Can I get an audible?
Yep, we can see your slides.
Thank you. Right, so I mean, everyone here must have heard of like self-driving cars and applications of computer vision from that angle. But part of my job, or like one of the main areas of what we do at Bensai, is to, similar to how, like you use computer vision in self-driving cars to understand the complex world. What we try to do at Bensai is to understand figures and all kinds of experiments that happen within scientific publication to try to extract relevant signals from them and try to inform scientists into how to make the experiments better and how to accelerate, how medicines come to the market. So that's a brief overview of what we do at Bensai. And just to go through like what I'm going to talk about today. So I'll take a very evolutionary kind of perspective on how computer vision is at the state it is today, and try to build up analogies and links to other fields, because computer vision is a very interdisciplinary field. I'll talk a little bit about, the hierarchy of how machine learning algorithms have grown up from a low level to a high level, such that now you can just take your phone and it unlocks just because it identifies your face from the camera. And finally, I'll talk about one of the, probably the most important tool for computer vision today, which is convolutional neural networks. And finally, hopefully we can spend a little bit of time just showing you how easy it is to set up code and get started with computer vision. So with that, let's get into like the very beginning of things, like let there be light kind of beginning. So when years and years ago, you had these animals probably in the depths of the oceans, what they used to do is they used to grab onto whatever was floating by, and they would eat it. And that's how things worked back then. But around 540 million years ago, some animals started evolving such that there were like light sensors, like they developed photosensitivity, and eventually they developed vision. And you can tell how important that was, because even now around more than 50% of your neurons in your brain are involved in visual processing. And it helps you do like pretty much everything. So manipulating objects around you, understanding things, and predicting what you'll do next, and things like that. And zoom forward many years later, we developed cameras around the 16th century, and digital cameras started coming around in the 1950s. 10 years later, work by a scientist called Hubert actually unraveled how visual processing in humans work. And that kind of inspired the whole field, along with some mathematical kind of insights. That is what inspired computer vision. Um, and today, around more than 80% of the internet traffic is probably videos in terms of bits. Sorry, I'm just looking at these lines and someone's trying to paint, but okay. So it becomes very important in today's world with the amount of data. It's like dark matter out there, to kind of try to understand this, huge amount of data that's flowing around, and to like try to make sense of it. And that's why computer vision today is probably one of the most researched topics in the world. And I would just draw your attention to the image on the right. And there is a lot going on actually when someone is taking a photo. So if you look at the graphic on top, a person is looking at the tree, and he makes a decision to take a photo. And essentially what I'm trying to show here is that we ourselves do a very layered kind of computer vision, in the sense that we see a tree and we identify the edges of the tree, and then understand what else is going on in the tree, and then kind of make an inference that there might be a penguin next to a tree. And yeah, so and that is basically what computer vision today is a parallel to what humans do. And kind of staying on that point, how vision works in humans is we have millions and millions of these photosensors called rods and cones in our brain, which detect very particular patterns. Some of these photosensors might detect straight lines, curved lines, circles, and so on. And and there is an electrical response that corresponds to how you process a certain image in front of you, or the world around you. And optical illusions are a very interesting thing to look at with this perspective, because I don't know if you're all in the chat, but you can maybe look at the image and try to let me know what you see. Because around 50% of, I found this on Twitter last week, around 50% of people actually see mild, while the rest of the people see wild. And what that tells you is that while your lower level, like both of you see the same image, where the edges and everything around the image is the same, the higher parts of your brain are very different. And so you both process it very differently. And that is an important point, and that relates to how, for example, you can build computer vision for drivers in a different way than you build computer vision for scientists. And yeah. So, and the early years of computer vision, and these algorithms are still popular today, was just that. It was like lower level processing. So there were edge detectors that sort of detected lines and it transforms on objects that try to find patterns using these things called filters, such that when you apply it on a particular part of the image, it matches. And so you know that there's a line there. And other algorithms, like if you want to look into the names SIFT, how line transform and so on. I wouldn't go into that much, but yeah. So um, talking more about like what visual recognition allows us to do. Like visual recognition is probably like the task most people are familiar with when it comes to computer vision. And most of them are related to identifying what the object or thing from a human perception point of view in the image is. So you can have things like classification, object detection, or semantic segmentation. And both are very closely linked to each other in terms of how you would build an algorithm to kind of do this. And yeah, so to solve this problem, probably like the most important tool today is something called convolutional neural networks, and they are surprisingly recent. I think 2012 was when the first ImageNet competition took place, and a convolutional neural net did really well on that. I think it was AlexNet. But yeah, a convolution neural net, I don't know how many of you are familiar with neural nets, but they're basically analogies to how neurons in your brain work, in the sense that they are these nodes interconnected. So a normal kind of standard neural network that we talk about is this fully connected neural network on the right-hand side of your screen. And so we call these also densely connected, in the sense that each node of one layer is connected to each node of the final layer. And essentially it goes from input to output when it does prediction. And when you're feeding it data to kind of learn patterns by induction in your data set, the signal goes from the right-hand side to the left-hand side. And that's a process called backpropagation. I won't get into that because I want to stick to more on the image side of things. So images are usually represented in this pattern as a matrix of numbers from 0 to 255, which represent, I think, linear color scale. And they usually have a number of channels to represent the different colors. Usually it goes red, green, blue, but here it's just a black and white image. So there you go. Again, like I won't get into the math too much, but just to give you a systemic kind of intuition about how things fit into each other. This is a general skeleton of how a convolutional neural net looks like. You have a fully connected layer, similar to how you would have in any other neural network at the end section, which is responsible mainly for like doing the classification. And you would have these three important layers. You have a convolutional layer, you have an activation, just like you have with the fully connected layer, or FC, on the right side. And you have something called a pooling layer, which I'll get into. So yeah, this is what a general neural net looks like. And uh, and you have many layers of this, and essentially like the convolution layers help to kind of extract features upon which the final layers of the model make their decision on, or run classification on. And to kind of look into what this convolution operation actually is, if I just go back to the slide here, it's a very similar algorithm to these edge detectors. in the sense that there is something called a filter, or it's often called a kernel. And essentially you take an input image and run this kernel along the input image, and you multiply the kernel, which you have selected here, into that particular section of the image. And that multiplication, so there's a little bit of algebra here, element-wise multiplication and sum, that creates this number 40 that you see on the right side. And you repeat this by moving the window along, and that's what gives you these values. And by choosing the right filter, you can detect the edges of the building, as you see here, or detect other features accordingly. And this part of this kernel and other things, so this kernel is a learned feature in a neural net that as you add more data to your data set and it looks at a picture of a dog, this kernel will start to change, update itself such that it picks out features that allows the final layer to make a decision on whether the image you're looking at is a cat or a dog. There are a few other details, like you can have padding on an image, which help on a convolution layer, which helps to uh, sort of have, like, sometimes what happens if you don't have padding is that the convolution filter loses information from the edges of the image. So if you add a little bit of padding, it retains that information. And you have a second thing called stride, which essentially is how you're moving the window along the image. So with a stride of 2, you're basically moving that kernel by 2 steps to the right or down. And finally, you have something called pooling. And this is useful to kind of, if you're, for example, this often happens like if your network is too big and you want to sort of reduce, the amount, you want to reduce this into more succinct representation, you would use average pooling, which essentially simply works by averaging a window. So here the window is 2, and so it would average 2 by 2 along your image or your next layer of convolution. And that's what I have. Do I have any questions so far before I move on to the demo?
So that whole thing was just processing images, pretty much, like pictures and stuff.
It's not just pictures. You can analyze all kinds of things. You can analyze videos. So I see a question. Can you explain stride again? Sure. So stride is essentially like, so usually when you move your window along the image, if stride is 1, you would just move the window by 1 number. But if stride is, for example, here it's 2, you move it along like 2 steps to the right. That's basically what stride is. I think it varies like what kind of research you want to do. I think the question is what level of mathematical background do you need? I think algebra, linear algebra, and a little bit of calculus are good enough to start working on these things. And a little few programming skills to kind of, make cool things and, build real things. Hi, Julia. Can you explain what you mean by analyze animal behavior? I think maybe if you look into some pet cameras, I'm sure they're already doing that. So if that's the answer, then there you go. Okay, so I think I'll move into the demo, and looking into the time, I don't know if I have enough time to code in real time, but I'll give it a shot. So if anyone is interested, I would encourage them to open Google Colab notebook such as this. And if you have a little bit of experience in Python, I think this part might be easier for you. But if you just want to see cool images or things, you know, a model that's learning in real time, then you can stick around too. So the first thing we'll do is sort of, this is admin work. You see if the libraries that you want in Python exist. So we would want, we'll do this in PyTorch and Torch Vision to get all the data that we need. And let's just run that. That works. While that's happening, okay, it looks like it's already there. So people familiar with here, just importing the libraries that we need, and maybe just import so this will allow us to like plot the images that we need. Right. So for this, what I'll do is we need a training data set. So this is normal process of machine learning. You need a training data set where, so here we'll go for this data set, which is basically identifying numbers from images. There are a few. Download this through so you can see the arguments. So this data, so this line sort of gives us the data set, and we need to convert it to something called a tensor. If you're not familiar with that, just Google it, because it basically means a high dimensional matrix where you can store and do the kinds of computation like the kernel and all the convolution operations that we showed earlier. Let's just copy that, and we'll have a test data set or a validation data set in this case, which is basically the ones that we will test our train model on. So let me print the length of these data sets. Let's see the size of these data sets. Oh, there you go. So while it's downloading that and showing us what the size of the it's doing that. So once you have the data sets, that worked, but once you have the data sets, you need data loaders. So you have a training data loader, which uses so you would give it your train data set, give it a batch size. So a batch is essentially how many images do you want to process at a single time. And let's shuffle this so we get random images. And you need a validation data loader, which is the same thing, basically, except it's for the validation set. So let's copy this over here. So it's like I'm rushing a bit because that where just to kind of, oh, I wrote this before, so I'll just copy this. This part of the code is just to show you what one image in the whole data set looks like. There you go. So this is what we'll be identifying in the code. And now let's do the actual neural net. So let's call it SuperPOSITRON net. So all neural nets are subclasses of this module. So this allows you to do forward and back propagation, which is used for training the model. So, okay, let's define the network now. So we need a convolution layer. So you would have dot star and dot d. The output channels. So that defines your basic convolution operation. I wish I could go into like the details, but we're short on time. So I think what I'm going to do is paste the remaining layers. So following this, you have a pooling layer. So you have so like we saw in the presentation, you have a convolution layer followed by a pooling layer, followed by an activation layer, and so just that stacked on 2 times. And following that, we have the classifier network or the dense fully connected layer, which is these 2 layers, and followed by a softmax layer, which basically fixes the range of your output between 0 and 1. So you get a probability output. And then just define like the forward function, which basically tells the network how to move the input along. So X here is our input, and we'll basically run it through all our convolution layers. If you can visualize the diagram, through the convolution layer, through the pooling layer, activation layer, and so on. And at the end of the convolution layers, the shape of the matrix is not flat, while the fully connected layers expect like a flat sort of tensor. And so we'll flatten it and then have the other layers next to it. Okay. And down here, let's define the network. You know what? I'll switch my screen because I've done the training already and we're short of time. But just to kind of show you what the training looks like. So once you've defined the network, And training is essentially you define a criterion, which is the loss function that you're trying to optimize. And you define an optimizer, which here is something called SGD, or stochastic gradient descent. And you give it the parameters of the model. You have a learning rate, which basically decides the gradient or the rate at which all the parameters or those numbers that you saw in the kernel will get updated during training. And it'll try to optimize this thing called cross entropy loss, which is basically a function that tells you how accurate you are. Basically, it looks at what the labels in the data set are, that it says this is true, but you predicted false. And so it increases the loss of that data. And for coding the training part, there's something called an epoch, which is basically one pass through all the data that you have, the training set. And so here we've gone for like 10 epochs. And essentially we pull data out of the data loader or the training set, and we run it through the model, and we kind of accumulate the loss. So if you see the output here, you can notice that the numbers start decreasing because your optimizer is learning the weights that actually give you a more accurate prediction. So you can see here on our validation set, which is down here, you can see that the accuracy initially is 54%. And as you go through the epochs, the loss value keeps decreasing. And you can see that the accuracy keeps increasing. And by the end of it, you have a model that's about, after 10 epochs or passes through the data, is around 92%. Oh, sorry, is it 90? Yeah, 92% accurate. And that's basically how you train a model. And down here, you can see that that image that we showed earlier, if you pass it through the model now, it predicts the number 7. That basically is what I was going to show.
All right. So thank you so much for that. And I know a lot of people, you guys are anxious to move on to our next workshop, but for those of you who are still here, thank you so much for paying attention. And I know definitely a lot of the code, it might have been a little bit fast. We will have this recording on YouTube. And also, I believe our speaker is on our Discord. So if you guys have any questions or want to chat, maybe that would be a better way. So yeah, without further ado, thank you so much for coming out here. And thank you so much to our speaker as well. So with that, we'll be closing off. If you guys want to move on to our next workshop, we'll welcome you there.